Welcome back. The goal of this video will be to define vector spaces, which are the fundamental objects of study in linear algebra. So we'll start by recalling Fn and its properties, and then we will abstract those properties in order to come up with a general definition. Recall that if F is a field, then we defined Fn to be the set of all ordered lists with entries x1 up to xn, where each entry xi is an element of the field F. We then defined two operations on Fn, namely addition and scalar multiplication. If we have two elements of Fn, so x1 up to xn and y1 up to yn, then we define their sum to be x1 plus y1, comma, and so on up to xn plus yn. So this is just component-wise addition. Next, we define the scalar multiplication. Given some lambda in our base field f, we can multiply it by an element of Fn, say x1, up to xn, as follows. We simply multiply each coordinate by lambda. And again, it's important to note that lambda lives in the field f, not in the set Fn. Finally, we see that scalar multiplication is similar to the addition in that it is also component-wise, as we multiply each component xi by lambda. The addition on Fn satisfies the following properties. First of all, it's associative, which means that x plus y plus z bracketed in this way is equal to x plus y plus z bracketed in the other way for all x, y, and z in Fn. So to give you an idea of why this is true, we can give a brief sketch of a proof. So if we call x x1 up to xn and y y1 up to yn and z z1 up to zn, then x plus y plus z bracketed in this way is equal, now if we just replace x, y, and z with the coordinate definitions we gave above, is equal to x1, xn, y1, yn, z1 up to zn. And now this has to be bracketed with the orange brackets in this way. Now, applying the definition of addition in Fn twice, what we get is a single ordered list which has as entries x1 plus y1 plus z1 bracketed in the following way. So x1 and y1 are bracketed together, and this holds for every entry. And so you can verify that this is indeed the case. And now, using the associativity of addition in our base field f, we can rearrange each coordinate to give x1 plus y1 plus z1, but now bracketed in the other possible way. And we do this in every coordinate. And now finally, we can undo the addition in order to get three ordered lists again. However, now we have that y and z are bracketed together, and this down here is simply x plus y plus z, but now bracketed in the other possible way. And this is what we wanted to show. As you can see, these associativity proofs are usually quite cumbersome because one has to work with three different elements, and so they're usually left as an exercise in textbooks. Second, the addition in Fn is commutative, which means that x plus y is equal to y plus x for all x and y in Fn. And we saw a proof of this in the last video. Third, addition in Fn also has a neutral element, which we can also call a zero in the case of the additive neutral element. So this means that there exists an element 0 in Fn such that x plus 0 is equal to x for all x in Fn. So this is simply an element that if we add it to some element x, we get back our original element x. And finally, we also have additive inverses. This means that for every x in Fn, there exists an x prime in Fn that satisfies x plus x prime is equal to 0. We will shortly see that this x prime is in fact uniquely determined by x, and so we can give it a name and we call it minus x. Next, we summarize the properties of scalar multiplication. So first, scalar multiplication is also associative. This means that lambda times mu times x equals lambda times mu times x. This holds for all lambda and mu in F and for all x in Fn. Here we have to be careful again because these lambda and mu's live in the field F, while this element x lives in Fn. And this means that this multiplication here is not a scalar multiplication, but actually multiplication in the field F, while the other operations, so this multiplication here is scalar multiplication in Fn, and this multiplication are also scalar multiplications in Fn. So what this equality is actually saying is that if we first multiply elements lambda and mu in the field F, and then follow up by a scalar multiplication with an element x, this is the same thing as first scalar multiplying the element mu with x, followed by scalar multiplying the element mu x with lambda. Next, we have that 1 in our field is a neutral element for scalar multiplication. So this means that 1 times x is equal to x for all x in Fn. We have to watch out again because this equation is deceptively simple. This 1 here is actually the multiplicative neutral element in our field F. So for example, in the field R, 1 would just be the usual number 1. Then what this equation is saying is that scalar multiplying the neutral element for multiplication in our field F with some element x of Fn just gives back that element x of Fn. So in other words, the multiplicative neutral element from our field F is also a neutral element for the scalar multiplication in Fn. We can give a proof of this property in one line. So if we take 1 times some element x1 up to xn, then by definition, this is just 1 times x1 and so on up to 1 times xn. And now what's happening here is that we have multiplication of an element x1 in the field with the neutral element 1 in the field, and so this just gives back x1. And this happens for each coordinate, so what we get back is just x1 up to xn. And now we see that if we call this element x, then this equation says that 1 times x is equal to x, which is precisely what we wanted to show. There's one last important property that ties addition and scalar multiplication together, namely the distributive property. this states that lambda times x plus y is equal to lambda times x plus lambda times y, and lambda plus mu times x is equal to lambda times x plus mu times x. And this holds for all x and y in Fn, and all lambda and mu in F. We again notice that lambda and mu are elements of the field F, while x and y are elements of Fn. In terms of operations, this addition here in the first equation is addition in Fn, while this multiplication is the scalar multiplication in Fn. While on the right-hand side, we have again addition in Fn and scalar multiplication in Fn as usual. So this first equation simply says that if I first add two elements of Fn and then scalar multiply them by a scalar lambda, then this is the same thing as if I first multiply each of the elements of Fn with a scalar lambda and then add them together. The second equation is a little more complicated, since the addition that's happening here is happening in the field F, while this multiplication is normal scalar multiplication in Fn. While on the right-hand side, the addition that's happening is addition in Fn, and these two multiplications are the normal scalar multiplication in Fn. So what the second equation is saying is that if I first add two scalars lambda and mu together in the field F, and then scalar multiply them with an element x, this is the same thing as if I separately scalar multiply x by lambda and mu and then add the results together. As was the case with previous properties, the proof of distributivity boils down to reducing the distributive property in Fn to the corresponding one in the field F. So let's prove the first equation. Suppose that x is equal to x1 up through xn, y is equal to y1 through yn, and that lambda is some element in F. Then, by the above, lambda times x plus y is equal to lambda times x1 up through xn plus y1 up through yn. Applying the definition of addition in Fn, we get that this equals lambda times x1 plus y1 all the way up through xn plus yn. Similarly, we can apply the definition of scalar multiplication in Fn to obtain that this equals lambda times x1 plus y1 all the way up to lambda times xn plus yn. Now we see that the operations in each coordinate, so the multiplication and the addition, are in fact multiplication and addition in F. And since multiplication distributes over addition in F, we can apply this rule to each coordinate to get that this is equal to lambda x1 plus lambda y1 all the way up to lambda xn plus lambda yn. To repeat, what we used here is the distributive property in the field F. We can now apply the definition of addition in reverse to separate out the terms that contain x and those that contain y. So what we end up with is lambda x1 all the way up to lambda xn plus lambda y1 all the way up to lambda yn. Now we may apply the definition of scalar multiplication to get the lambda out of the expression, so that we have lambda times x1 up through xn plus lambda times y1 up through yn. And this now replacing x1 through xn by x and y1 through yn by y is just lambda x plus lambda y. And this is what we wanted to show. So we proved the first equation and now can move on to the second, which is similar. So we suppose that lambda and mu are elements in our field F, and that x equals x1 up through xn is an element of Fn. Now, lambda plus mu times x equals, by the above, lambda plus mu times x1 all the way up through xn. Applying the definition of scalar multiplication, we get that this equals lambda plus mu times x1, and so on up through lambda plus mu times xn. Looking at an arbitrary coordinate, we again see that the operations here are just happening in F, and we know that multiplication distributes over addition in F, so applying that we get that this is equal to lambda times x1 plus mu times x1, and so on, up to lambda times xn plus mu times xn. And this is again applying the distributive property in our field F. Now we can separate out the components containing lambda from those containing mu using the definition of addition in reverse. This gives lambda x1 up to lambda xn plus mu x1 up to mu xn. Finally, we can use the definition of scalar multiplication in reverse to get lambda times x1 up through xn plus mu times x1 through xn, and this is just lambda times x plus mu times x, and this is what we wanted to show. We should now be able to appreciate the definition of a vector space. A vector space over a field F is a set V with two operations. We need an addition. This is a function from V cross V to V, and it maps elements V and W in V to their sum, V plus W. And then we also need a scalar multiplication, which is a function from F cross V to V. And this takes a scalar in F and an element of V and maps it to the scalar multiple lambda V. By now we should be familiar with the fact that the addition adds two elements of the vector space, while scalar multiplication takes an element of the vector space and multiplies it by a scalar, which is an element of the field F. We require these operations to satisfy the following properties. First, we want addition to be associative, so u plus v plus w, bracketed in this way, should be equal to u plus v plus w, bracketed in the other conceivable way, for all u, v, and w in V. Next, we also want addition to be commutative, so u plus v should equal v plus u for all u, v, and v. And then we also want a neutral element for the addition, so there exists some element 0 in V, such that v plus 0 is equal to v for all elements v in the set V. And finally, we would like additive inverses. So for all v in the set V, there exists some w in V such that v plus w is equal to 0. Next, we turn to the scalar multiplication, which we would also like to be associative. So this means that lambda times mu times v is equal to lambda times mu times v for all lambda mu in F and for all v in V. And secondly, we would like that the unit element with respect to multiplication in our field f is also a unit with respect to scalar multiplication in our vector space. So 1 times v should equal v for all v in v. Now the last axioms that we'll list will ensure that the addition and the scalar multiplication interact nicely together. And this will be the distributive properties. So we want that lambda times u plus v is equal to lambda u plus lambda v. And this is for all lambda in f and for all u and v in the set v. And then there's another way that we could have distributivity, namely if we first add two elements in f, so lambda plus mu times v should be equal to lambda v plus mu times v. And this is again for all lambda and mu in f and for all v in the set v. In summary, we define a vector space over a field f to be a set with two operations, addition and scalar multiplication. And we want the addition to be associative, commutative, have a neutral element 0, and have inverses. And we want the scalar multiplication to be associative, and we want that the multiplicative unit in f1 is also a unit for the scalar multiplication. And finally, we want that the addition and the scalar multiplication interact nicely with each other, so we have two distributive properties corresponding to the two ways we could possibly have addition and multiplication mixing in the vector space. To introduce some terminology, we call elements of V vectors, and when the field F is R, we call a vector space over R a real vector space, and when the field F is C, we call the vector space a complex vector space. This brings us to our first example of a vector space, which is Fn, which is a vector space over F. What we did in the first part of this video was essentially a proof of the fact that Fn is indeed a vector space over F. But let's quickly go through the points in the definition again to make sure we believe this. So first, we have an addition on Fn, which is the component-wise addition of vectors. Then we have a scalar multiplication on Fn, which is defined by multiplying each component with the scalar lambda. As we've seen in the first part of the video, the addition on Fn is associative, it's commutative, and we have a neutral element as well as inverses. And we also saw that scalar multiplication is associative and that the multiplicative unit in f is also a neutral element for the scalar multiplication. And finally, we also confirmed the distributive properties for Fn. And all of this together shows that indeed Fn is a vector space over F, and it'll be the most important example of such a vector space. This neatly summarizes what we've done so far, and in the next video we'll see many more examples of vector spaces, and I hope to see you then.